Have you ever dreamed of traveling across the universe in the blink of an eye? Not in a starship that takes thousands of years, but through a cosmic shortcut, a tunnel through space-time itself. This isn't just a fantasy from your favorite sci-fi movie. It's a mind-bending concept born from the heart of modern physics, the wormhole. Today, we are diving deep into the fabric of reality to explore these incredible cosmic bridges. Where did the idea come from? Could they actually exist? And what would it mean for humanity if we ever found one? The story of the wormhole begins, like so many stories in modern physics, with Albert Einstein. Back in 1915, his theory of general relativity completely revolutionized our understanding of gravity. He showed us that space and time are not separate, static entities, but are woven together into a single, dynamic fabric called space-time. Massive objects, like stars and planets, don't just sit in this fabric, they warp and curve it. And this curvature is what we experience as gravity. It's why planets orbit stars and why an apple falls to the ground. But Einstein's equations were far richer and more mysterious than even he initially realized. They held secrets, mathematical oddities that pointed to phenomena so strange they sounded like science fiction. One of these was the black hole, a region of space-time so warped by immense gravity that nothing, not even light, can escape. But what if there was an opposite? In 1935, Einstein and his colleague Nathan Rosen were exploring these very equations. They discovered a peculiar solution, a mathematical bridge connecting two different points in space-time. Imagine taking a sheet of paper, marking two distant points, and then folding the paper so the points touch. You've just created a shortcut. The Einstein-Rosen Bridge, as it was called, was the theoretical equivalent of this, a tunnel connecting two separate regions of the universe, or even two different universes entirely. This was the birth of the wormhole. The original Einstein-Rosen Bridge, however, had a major problem. It was incredibly unstable. The throat of the wormhole would snap shut the instant anything tried to pass through it. It was like a door that slams closed the moment you try to walk through. For decades, wormholes remained a mathematical curiosity, a fascinating but seemingly impossible feature of the cosmos. They were relegated to the realm of theoretical physics, fun to think about but not something anyone expected to actually find or use. Then came the science fiction writers. From Star Trek and its transporter beams to Stargate and its interstellar gateway, pop culture embraced the wormhole as the ultimate travel solution. It allowed heroes to hop between galaxies, bypassing the immense, light-year-long distances that make interstellar travel so daunting. These stories captured our imagination and made us wonder, what if? What if there was a way to make these cosmic shortcuts stable? This question brought wormholes back into the scientific spotlight in the 1980s. Physicist Kip Thorne, who was a scientific advisor for the movie Contact, was challenged by astronomer Carl Sagan to devise a plausible way for a character to travel across the galaxy. Thorne and his colleagues took the challenge seriously. They realized that to keep a wormhole open, you would need something truly bizarre, a substance with negative energy density. Now, what on earth is negative energy? In our everyday world, everything has positive energy and positive mass. Gravity, as we know it, is always attractive. But this theoretical exotic matter would have anti-gravitational properties. It would push space-time apart instead of pulling it together. If you could line the throat of a wormhole with this exotic matter, it could theoretically prop it open, creating a stable, traversable passage. Suddenly, wormholes weren't just a fantasy. They had a potential, albeit highly speculative, physical basis. The problem is, we have never observed exotic matter. While some quantum effects like the Casimir effect hint at the existence of negative energy on a microscopic scale, no one knows if it is possible to gather enough of it to stabilize a macroscopic wormhole large enough for a person or a spaceship. It remains one of the biggest hurdles for the reality of wormholes. So, let's play a game of what if. What if we found a wormhole, or even figured out how to build one? The implications would be staggering. A trip to the nearest star system, Proxima Centauri, which would take a conventional rocket tens of thousands of years, could be reduced to a short stroll through a cosmic tunnel. We could explore distant galaxies, witness the birth of stars, and search for life on countless exoplanets. The entire universe would become our neighborhood. But it gets even weirder. Because wormholes connect two points in space-time, they might not just connect different places, but also different times. By manipulating the ends of a wormhole, for example, by taking one end on a high-speed journey and then bringing it back, it might be possible to create a time machine. You could step into one end of the wormhole in the year 2024 and step out the other end in 2124, or even 1924. This, of course, opens a huge can of worms, full of paradoxes. What if you went back in time and accidentally prevented your own parents from meeting? This is the famous grandfather paradox. Many physicists, including Stephen Hawking, proposed a chronology protection conjecture, suggesting that the laws of physics themselves would conspire to prevent such paradoxes from happening. Perhaps the wormhole would collapse, or radiation feedback would destroy anything that tried to pass through. The universe, it seems, might have its own built-in safety mechanisms to protect the integrity of cause and effect. So where does this leave us? Are wormholes real? The honest answer is, we don't know. They remain a beautiful, fascinating, and unproven prediction of general relativity. To truly know, we would need to merge Einstein's theory of gravity with the world of quantum mechanics into a unified theory of everything. Such a theory might tell us whether exotic matter is real and if spacetime can truly be stitched together in this extraordinary way. Until then, we can search for clues. Some scientists have suggested that wormholes might have observable signatures. For instance, the way a wormhole's gravity bends the light from a star behind it would be different from a black hole. We could potentially look for these gravitational lensing effects. Or, perhaps, some of the supermassive black holes we see at the centers of galaxies are actually the mouths of enormous wormholes. The journey from a mathematical curiosity in Einstein's equations to a staple of science fiction. And a serious topic of scientific debate is a testament to the power of human imagination and our relentless quest to understand the cosmos. Wormholes represent the edge of our knowledge, a place where the rules of reality become blurry and the possibilities seem endless. They remind us that the universe is far stranger and more wonderful than we can possibly imagine. Whether they turn out to be real cosmic subways or just a beautiful mathematical dream, the search for them pushes us to ask deeper questions about the very nature of space, time, and our place within it all. Thanks for joining us on this journey through spacetime. If you enjoyed this exploration of the cosmic unknown, don't forget to like, share, and subscribe for more deep dives into the mysteries of the universe. What topic should we explore next? Let us know in the comments below. Until next time, keep looking up.